In theoretical physics and mathematical physics, analytical mechanics, or theoretical mechanics is a collection of closely related alternative formulations of classical mechanics. It was developed by many scientists and mathematicians during the 18th century and onward, after Newtonian mechanics. Since Newtonian mechanics considers vector quantities of motion, particularly accelerations, momenta, forces, of the constituents of the system, an alternative name for the mechanics governed by Newton's laws and Euler's laws is vectorial mechanics. By contrast, analytical mechanics uses scalar properties of motion representing the system as a whole, usually its total kinetic energy and its potential energy, not Newton's vectorial forces of individual particles. A scalar is a quantity, whereas a vector is represented by quantity and direction. The equations of motion are derived from the scalar quantity by some underlying principle about the scalar's variation. Analytical mechanics takes advantage of a system's constraints to solve problems. The formalism is well suited to arbitrary choices of coordinates, known in the context as generalized coordinates. The kinetic and potential energies of the system are expressed using these generalized coordinates or momenta, and the equations of motion can be readily set up. Thus, analytical mechanics allows numerous mechanical problems to be solved with greater efficiency than fully vectorial methods. It does not always work for non-conservative forces or dissipative forces like friction, in which case one may revert to Newtonian mechanics, or use the Udway-Diakalaba equation. Two dominant branches of analytical mechanics are Lagrangian mechanics and Hamiltonian mechanics. Both formulations are equivalent by a Legendre transformation on the generalized coordinates, velocities, and momenta. Therefore both contain the same information for describing the dynamics of a system. There are other formulations such as Hamilton-Jacobi theory, Ratheon mechanics, and Appel's equation of motion. All equations of motion for particles and fields, in any formalism, can be derived from the widely applicable result called the principle of least action. One result is Noether's theorem, a statement which connects conservation laws to their associated symmetries. Analytical mechanics does not introduce new physics and is not more general than Newtonian mechanics. Rather, it is a collection of equivalent formalisms which have broad application. In fact, the same principles and formalisms can be used in relativistic mechanics and general relativity, and with some modification, quantum mechanics and quantum field theory also. Analytical mechanics is used widely, from fundamental physics to applied mathematics, particularly chaos theory. The methods of analytical mechanics apply to discrete particles, each with a finite number of degrees of freedom. They can be modified to describe continuous fields or fluids, which have infinite degrees of freedom. The definitions and equations have a close analogy with those of mechanics. Intrinsic motion, generalized coordinates and constraints. In Newtonian mechanics, one customarily uses all three Cartesian coordinates, or other 3D coordinates system, to refer to a body's position during its motion. In physical systems, however, some structure or other system usually constrains the body's motion from taking certain directions and pathways. So a full set of Cartesian coordinates is often unneeded, as the constraints determine the evolving relations among the coordinates, which relations can be modeled by equations corresponding to the constraints. In the Lagrangian and Hamiltonian formalisms, the constraints are incorporated into the motion's geometry, reducing the number of coordinates to the minimum needed to model the motion. These are known as generalized coordinates, denoted chi. Difference between curvilinear and generalized coordinates. Generalized coordinates incorporate constraints on the system. There is one generalized coordinate chi for each degree of freedom, i.e., each way the system can change its configuration, as curvilinear lengths or angles of rotation. Generalized coordinates are not the same as curvilinear coordinates. The number of curvilinear coordinates equals the dimension of the position space in question, while the number of generalized coordinates is not necessarily equal to this dimension. Constraints can reduce the number of degrees of freedom. Following the general rule, dimension of position space times number of constituents of system minus equals for a system with n degrees of freedom. The generalized coordinates can be collected into an n-tuple, and the time derivative of this tuple give the generalized velocities. D'Alembert's principle. The foundation which the subject is built on is D'Alembert's principle. This principle states that infinitesimal virtual work done by a force across reversible displacements is zero, which is the work done by a force consistent with ideal constraints of the system. The idea of a constraint is useful, since this limits what the system can do, and can provide steps to solving for the motion of the system. The equation for D'Alembert's principle is, where are the generalized forces and q are the generalized coordinates. This leads to the generalized form of Newton's laws in the language of analytical mechanics, where T is the total kinetic energy of the system, and the notation is a useful shorthand. Holonomic constraints. If the curvilinear coordinate system is defined by the standard position vector r, and if the position vector can be written in terms of the generalized coordinates q and time t in the form, and this relation holds for all times t, then q are called holonomic constraints. Vector r is explicitly dependent on t in cases when the constraints vary with time, not just because of q. For time-independent situations, the constraints are also called scleronomic. For time-dependent cases they are called rheonomic. Lagrangian mechanics. Lagrangian and Euler-Lagrange equations. The introduction of generalized coordinates and the fundamental Lagrangian function, where T is the total kinetic energy and V is the total potential energy of the entire system. Then either following the calculus of variations or using the above formula, lead to the Euler-Lagrange equations, which are a set of n second-order, ordinary differential equations, one for each chi. This formulation identifies the actual path followed by the motion as a selection of the path over which the time integral of kinetic energy is least, assuming the total energy to be fixed, and imposing no conditions on the time of transit. Configuration space. The Lagrangian formulation uses the configuration space of the system, the set of all possible generalized coordinates, whereas n-dimensional real space. The particular solution to the Euler-Lagrange equations is called a path or trajectory, i.e., one particular q subject to the required initial conditions. The general solutions form a set of possible configurations as functions of time. The configuration space can be defined more generally, and indeed more deeply, in terms of topological manifolds and the tangent bundle. Hamiltonian mechanics. Hamiltonian and Hamilton's equations. The Legendre transformation of the Lagrangian replaces the generalized coordinates and velocities with the generalized coordinates and the generalized momenta conjugate to the generalized coordinates, and introduces the Hamiltonian, where denotes the dot product, also leading to Hamilton's equations, which are now a set of two n first-order ordinary differential equations, one for each chi and pi. Another result from the Legendre transformation relates the time derivatives of the Lagrangian and Hamiltonian, which is often considered one of Hamilton's equations of motion additionally to the others. The generalized momenta can be written in terms of the generalized forces in the same way as Newton's second law. Generalized momentum space. Analogous to the configuration space, the set of all momenta is the momentum space. Momentum space also refers to k-space, the set of all wave vectors as used in quantum mechanics and theory of waves. This is not referred to in this context. Phase space. The set of all positions and momenta form the phase space, that is, the Cartesian product times of the configuration space and generalized momentum space. A particular solution to Hamilton's equations is called a phase path, a particular curve P, subject to the required initial conditions. the set of all phase paths. The general solution to the differential equations is the phase portrait. The Poisson bracket. All dynamical variables can be derived from position r, momentum p, and time t, and written as a function of these. R equals A. If A and B are two scalar-valued dynamical variables, the Poisson bracket is defined by the generalized coordinates and momenta. Calculating the total derivative of one of these, say A, and substituting Hamilton's equations into the result leads to the time evolution of A. This equation in A is closely related to the equation of motion in the Heisenberg picture of quantum mechanics, in which classical dynamical variables become quantum operators, and the Poisson bracket is replaced by the commutator of operators via Dirac's canonical quantization. Properties of the Lagrangian and Hamiltonian functions. Following are overlapping properties between the Lagrangian and Hamiltonian functions. All the individual generalized coordinates chi, velocities qi and momenta pi for every degree of freedom are mutually independent. Explicit time dependence of a function means the function actually includes time t as a variable in addition to the q, p, not simply as a parameter through q and p, which would mean explicit time independence. The Lagrangian is invariant under addition of the total time derivative of any function of q and t, that is, so each Lagrangian L and L describe exactly the same motion. In other words, the Lagrangian of a system is not unique. Analogously, the Hamiltonian is invariant under addition of the partial time derivative of any function of q, p and t, that is, this property is used in canonical transformations. If the Lagrangian is independent of some generalized coordinates, then the generalized momenta conjugate to those coordinates are constants of the motion, i.e., are conserved. This immediately follows from Lagrange's equations. Such coordinates are cyclic or ignorable. It can be shown that the Hamiltonian is also cyclic in exactly the same generalized coordinates. If the Lagrangian is time-independent, the Hamiltonian is also time-independent. If the kinetic energy is a homogeneous function of degree 2 of the generalized velocities, and the Lagrangian is explicitly time-independent, then, where lambda is a constant, then the Hamiltonian will be the total conserved energy, equal to the total kinetic and potential energies of the system. This is the basis for the Schrödinger equation. Inserting quantum operators directly obtains it. Principle of least action. Action is another quantity in analytical mechanics defined as a functional of the Lagrangian. A general way to find the equations of motion from the action is the principle of least action, where the departure t1 and arrival t2 times are fixed. The term path or trajectory refers to the time evolution of the system as a path through configuration space. In other words, Q tracing out a path in the path for which action is least is the path taken by the system. From this principle, all equations of motion in classical mechanics can be derived. This approach can be extended to fields rather than a system of particles, and underlies the path integral formulation of quantum mechanics, and is used for calculating geodesic motion in general relativity. Hamiltonian Jacobi mechanics. Canonical transformations. The invariance of the Hamiltonian allows the Hamiltonian in one set of coordinates q and momenta p to be transformed into a new set q equals q and p equals p, in four possible ways, with the restriction on p and q such that the transformed Hamiltonian system is. The above transformations are called canonical transformations. Each function Gn is called a generating function of the nth kind, or type n. The transformation of coordinates and momenta can allow simplification for solving Hamilton's equations for a given problem. The choice of Q and P is completely arbitrary, but not every choice leads to a canonical transformation. One simple criterion for a transformation Q and PP to be canonical is the Poisson bracket be unity, for all I equals 1, 2, n. If this does not hold, then the transformation is not canonical. The Hamilton-Jacobi equation, by setting the canonically transformed Hamiltonian k equals 0, and the type 2 generating function equal to Hamilton's principal function plus an arbitrary constant c, the generalized momenta become, and p is constant, then the Hamiltonian-Jacobi equation can be derived from the type 2 canonical transformation, where h is the Hamiltonian as before. Another related function is Hamilton's characteristic function, used to solve the HJE by additive separation of variables for a time-independent Hamiltonian h. The study of the solutions of the Hamilton-Jacobi equations leads naturally to the study of symplectic manifolds and symplectic topology. In this formulation, the solutions of the Hamilton-Jacobi equations are the integral curves of Hamiltonian vector fields. Ratheon mechanics. Ratheon mechanics is a hybrid formulation of Lagrangian and Hamiltonian mechanics, not often used but especially useful for removing cyclic coordinates. If the Lagrangian of a system has s cyclic coordinates, q equals q1, q2, qs with conjugate momenta p equals p1, p2, ps, with the rest of the coordinates non-cyclic and denoted zeta equals zeta1, zeta1, zeta n-s, they can be removed by introducing the Ratheon, which leads to a set of 2s Hamiltonian equations for the cyclic coordinates q, and n-s Lagrangian equations in the non-cyclic coordinates zeta. Set up in this way, although the Ratheon has the form of the Hamiltonian, it can be thought of a Lagrangian with n-s degrees of freedom. The coordinates q do not have to be cyclic. The partition between which coordinates enter the Hamiltonian equations and those which enter the Lagrangian equations is arbitrary. It is simply convenient to let the Hamiltonian equations remove the cyclic coordinates, leaving the non-cyclic coordinates to the Lagrangian equations of motion. Appelian mechanics. Appel's equation of motion involve generalized accelerations, the second-time derivatives of the generalized coordinates, as well as generalized forces mentioned above in D'Alembert's principle. The equations are where is the acceleration of the k particle, the second-time derivative of its position vector. Each acceleration ak is expressed in terms of the generalized accelerations alpha r. Likewise, each rk are expressed in terms the generalized coordinates qr. Extensions to classical field theory. Lagrangian field theory generalized coordinates apply to discrete particles. For n-scalar fields phi I where I equals 1, 2, and the Euler-Lagrange equations have an analog for fields, where mu denotes the foregradient and the summation convention has been used. For n-scalar fields, these Lagrangian field equations are a set of n second-order partial differential equations in the fields, which in general will be coupled and nonlinear. This scalar field formulation can be extended to vector fields, tensor fields, and spinor fields. The Lagrangian is the volume integral of the Lagrangian density. Originally developed for classical fields, the above formulation is applicable to all physical fields in classical, quantum, and relativistic situations, such as Newtonian gravity, classical electromagnetism, general relativity, and quantum field theory. It is a question of determining the correct Lagrangian density to generate the correct field equation. Hamiltonian field theory. The corresponding momentum field densities conjugate to the n-scalar fields phi ir, where in this context the overdot denotes a partial time derivative, not a total time derivative. The Hamiltonian density is defined by analogy with mechanics. The equations of motion are, where the variational derivative must be used instead of merely partial derivatives. For n fields, these Hamiltonian field equations are a set of two n first-order partial differential equations, which in general will be coupled and nonlinear. Again, the volume integral of the Hamiltonian density is the Hamiltonian symmetry, conservation, and Noether's theorem. Symmetry transformations in classical space and time. Each transformation can be described by an operator. The following are the cases when the operator does not change R or P, i.e., symmetries, where R is the rotation matrix about an axis defined by the unit vector n and angle theta. Noether's theorem. Noether's theorem states that a continuous symmetry transformation of the action corresponds to a conservation law, i.e., the action doesn't change under a transformation parameterized by a parameter S. The Lagrangian describes the same motion independent of S, which can be length, angle of rotation, or time. The corresponding moment at a q will be conserved.